So uses of the cross product, one geometric use is to calculate the parallelogram, the area of a parallelogram and the area of a parallelepiped. So to start with the parallelogram in 2 dimensions, if we have 2 vectors A and B, we can imagine these things forming a parallelogram where A is the base vector, B is the side vector. And if they have this common initial point, then we can sort of fill in the rest in red here and form this parallelogram. So in that sense, we can talk about the parallelogram formed by 2 vectors. Now, if we look here, this is the angle theta between the vectors A and B. And we consider what this altitude is, or this height. Well, the sine of theta right here is equal to the opposite x over the hypotenuse magnitude of b. Okay, so that means that x, this unknown side, is equal to magnitude of b times sine theta. That's exactly that situation. So that's where that comes about in this formula. And if we recall, we know the height of a parallelogram and we know the length of its base, then we can calculate its area with base times height. Okay, but we know also previously that this expression is exactly equal to the magnitude of the cross product. So this helps us out quite a bit. So we could use the cross product to find this parallelogram area. So in that sense, the cross product helps us to find parallelogram areas, or it's one step away by just taking the magnitude of the cross product vector. Okay, so the problem below says we're given 3 points. We're asked to find a vector orthogonal to the plane that contains those 3 points, and then also find the area of the triangle formed by P, Q, and R. Okay, so using A cross B to find such a vector, we need 2 vectors A and B to find this vector that's orthogonal to the plane containing these 3 points. So in order to find that, first we need to come up with 2 vectors with a common initial point, and any of those 3 points will do as the common initial point. So we'll choose P arbitrarily. And that means we'll take A to be Q minus P and B to be R minus P. And this is just component-wise calculation of what the vector components are. So Q's 4 minus P's 0, 2 minus 0, 0 minus negative 3. And that gives us the vector A. We do the same thing for B, doing R minus P. And we get A and B as our vectors here. Okay, the next thing we'll do is we'll compute A cross B, and we'll take its magnitude all in one shot. But one thing we could do, we could set this up. A cross B is equal to the magnitude of the determinant of A cross of this 3 by 3 matrix right here. Done the same way we've been taking the cross product for all the previous examples. All right, so this vector comes out to be -1, -7, 6. The reader can verify that by computing that cross product on their own. By the way, this is part of our answer, so I'll write it down below. -1, -1, -7, 6 is orthogonal to the plane containing those 3 points. Next up, we just find its magnitude to find A cross B. And well, that magnitude is this value of root 86. Okay, so that tells us that the area of the parallelogram formed by these 2 vectors is root 86. Well, if we think about what these 2 vectors might be doing in terms of a triangle that's involved with P, Q, and R, remember that this was P, and one of these is Q and the other one's R. It doesn't really matter. We connect these 2 things. We have a triangle here. That's the triangle whose area we're looking at. But if we remember that there's a parallelogram involved in this, that parallelogram is twice the area of each of these triangles. So we just take half the area of the parallelogram, which is 1/2 square root of 86, and we have the area of the triangle PQR. So those are the basic steps to this problem without all the details being shown. The reader's encouraged to go through and fill in at least this calculation right here, and the rest is pretty well obvious. So let's see one more application of this involving parallelopipeds. So this is called the scalar triple product, A dot B cross C, and then taking the absolute value of that, not the magnitude, but the absolute value of this result. So now if we have three vectors, A, B, and C, this is A pointing upward, tilting off to the right, so it's not quite perpendicular to the plane of B and C. We've got a vector V, or B, pointing off into the page. We've got a vector C pointing more or less parallel with the plane of the page. So in red, we've sketched in the parallelogram that's formed more or less by these three vectors, or the parallelopiped actually. So a parallelopiped is the three-dimensional version of a parallelogram. Think of it as a box that's been kicked or partially squashed. So now we see how that comes about. Remember that B cross C is a vector perpendicular to the plane containing B and C. So that's a really nice tool. Well, that in fact is going to tell us the height of this situation, or at least the perpendicularity of this vector that's perpendicular to the plane of B and C. So B cross C is this vector here, and if we dot that with the vector A and take the magnitude of it, we'll get the volume of this parallelepiped. There's a little bit more to the proof of that, or to the argument that that is, or why that's the volume of this thing, but without going into too many details, we can just leave this alone for now. So if we're given three vectors U, V, and W, and we're asked to find the volume of the parallelepiped formed by these vectors, well, it doesn't matter who's who, but we'll set it up as U dotted with V cross W. Here's V cross W as a matrix. We'll find the determinant of that. The result of that is this vector, and we dot that with the vector U, taking the absolute value at the end of it all, and we end up with 1. The volume contained in that parallelepiped then is 1. The reader can verify some of those calculations, the dot product and the cross product namely, and see that that's all actually the case. Well, in fact, the cross product is verified down here. So volume of a parallelepiped is the scalar triple product. Okay, last is a physical application. So torque. Torque will commonly associate rotation with the cross product, and torque is a rotational motion. So torque is the force that's applied radially to something. So tau represents the torque, R represents the position vector along a radial line, and F is a force which represents force acting on the end of this radial line, whatever object we might be considering. So remember that R cross F, the magnitude of that is actually equal to magnitude R, magnitude F, sine theta. It's a very useful thing to have around because if we know one or the other, just the two vectors R and F, or their magnitudes and the angle between them, well, then we can calculate torque from this, okay? And that's exactly what we'll use down below. We just want to find the magnitude of the torque. Finding the vector is a little bit more work. I don't think any problems are going to involve that in the exercises, so we'll leave this as is. Now, here's our situation. We're tightening a bolt with a 30 Newton force applied to the end of a 0.2 meter wrench with an angle of 60 degrees between the force vector and the position vector. The position vector essentially runs along the length of the wrench. So we'll see that here. This is R, and then we're applying a force F at an angle theta to this position vector, radially away from the bolt that we're tightening with the wrench. Okay, so we've got all the pieces we need. F is 30 newtons, well, at least magnitude of F is 30 newtons. R is 0.2 meters, its magnitude is 0.2 meters, and theta is 60 degrees. There's not a whole lot of work to do here. We want the torque, So we use this formula because we know the angle theta. We know R's magnitude. We know F's magnitude. Sine of 60 is √3/2. This is a 6. And in the end, we'll round this to a few decimal places. And we end up with 5.196 Newton meters. And we'll leave it at that. Okay, so that is a torque application. And that concludes section 10.4.